Okay, today's lesson is going to be about the graphs of exponential functions. In order to figure out what those look like, let's not forget that exponential means that f of x is equal to some base to the exponent x. We're going to also be transforming this one around, so we're also going to be looking at the new function that has a b to the k bracket x minus h squared plus c. So we're going to look at what all these little things do as well. But before we even start that, let's take a look about what the different bases is going to mean when we go to graph. So in order to figure out how the base affects the graph, let's look at this in Desmos. So if I have a base of, say, 2, it's going to look like this. If I have a base of 5 to the exponent x, well, it now looks like that. All right, let's go even bigger. Let's have a function where 10 is the base to the exponent x. Oh my goodness. So notice that as the base gets bigger, my graph gets steeper and steeper. So let's write that down. Okay, so we just looked at 2 to the x versus 5 to the x versus 10 to the x. So this red curve here was my 2 to the x. The green curve was my 5 to the x. And my blue curve was my 10 to the x. So we can see what's happening here is that as the base increases, the graph gets steeper faster. So we say it's growing faster. And these are all examples of what we call exponential growth. Okay. Now let's notice a few more things about these ones. Notice that my y-intercept is always the same value. So far I've got y-intercept is equal to 1 every time. Okay. And notice that not once has it crossed the x-axis. So that's really important too. We have no x-intercepts. Oops, too far. No x-intercepts. So for each one of these, we have the same domain and range for each one. So that's kind of interesting too. So if I were to write out my domain and range for these ones, they're all going to be for domain, x is any real number, because I can put anything I want in as my exponent. But for range, notice that y is any real number, but y must be greater than 0. Never equals 0. That's right there where that y equals 0. That is what we call an asymptote. Okay, so an asymptote is a funny looking word. Asymptote equals a line that the graph approaches but never touches or crosses. It never crosses it. It never touches it. It never crosses it. So for these guys, y equals 0 is the asymptote, because it never crosses the x-axis. Okay, so now let's look at a few more and see what else we see. Okay, this time I want to look at 3 different functions again, and this time I want to look at when f of x is equal to 1/2 x. I want to look at when g of x is equal to 1/5 to the exponent x. And let's look at h of x, which is 1/10 all to the exponent x. And what did we just see happening here? Well, that's interesting. My 1/2 x is down here. My 1/5 is steeper. My 1/10 is steeper again. So that's interesting. Notice how they're also now on this side of the y-axis. And instead of going up, we are now going down. Interesting. Okay, so let's take a look here. I've got the two sets of graphs side by side so we can get a better look at it. And let's just remember that this first graph here, that was my 1/2 all to the x. The next one was the 1/5 all to the x. And this last one here, that was my 1/10 all to the x. So what's happening when I have a fraction base? This is pretty interesting. Let's see. So now that my base is a fraction, we see that the graph goes down. So we call that exponential decay. Whoa, nice spelling. Exponential decay. The graph has gone down, and we see that the smaller the fraction, right, because 1/10 is smaller than 1/2, the faster the decay. So that's pretty interesting. Notice how we also have the same asymptote. So our asymptote is also asymptote at y = 0 because the graph never crosses the x-axis. And notice that y = 1 is the y-intercept again. So it's still y = 1 is the y-intercept, just like it was over here. And why is that? Let's remember that anything to the exponent 0 equals 1. So anything to the exponent 0 equals 1. So there's why my y-intercept is equal to 1. Okay. Let's also not forget our domain and range for this one. So just like before, we're going to have the same domain and range for this one. We have a domain where x is any real number, and we have a range where y is any real number, such that y is greater than 0, right? Because it's all above the x-axis, it just never touches the x-axis. Good. Okay, now that we figured out what the base does, it makes it grow faster, it makes it come down slower. Let's look at what happens when we stick stuff around the base. So right now I'm just going to focus on 2 to the x, and we're going to kind of play with it, and we're going to see what happens. So here's what 2 to the x looks like. Well, if I went to type in maybe a number in front of the 2x, let's maybe say it's 4 to the 2 to the exponent x. Whoa, where did my y-intercept just go? Ooh, my y-intercept is that number that's in front. So that's an important thing to notice. Okay, so the number in front of the base becomes my y-intercept. So that's important. Let's change where my number is. So now let's put that number maybe at the end and say plus 4 at the end. So what have I done? I have now picked everything up and I've pushed my function up higher. So what I've done is I've just done a translation up. So I've done a vertical translation. Okay, so when we add or subtract a number out at the outside here, that means it's a vertical translation. And just like with our quadratics, if I have plus, I go up. If I had a minus, it would go down. So let's see that one. Equals 2 to the exponent x minus 4 would drop it down. And notice that the asymptotes are going to go too. So instead of being at x is equal or y is equal to 0, we're going to have one that's now at -4 for the one that went down. And my other asymptote for the first one would have been at +4. So that +4 on the outside or that -4 on the outside, that's also going to tell me where my new asymptote is going to be. Asymptote equals the number that was added or subtracted. So these are good things to notice. Okay, so I just labeled up our picture here. So our asymptote becomes the number that was on the outside. Our original asymptote was y equals 0, and y equals -4 was our new asymptote. So that would be our vertical translation. Let's see if we can't find a horizontal translation. So let's see if we can't figure out what horizontal translations are going to look like. So again, I have my base function 2 to the x. To type it into Desmos, we have to do it in the brackets up in the exponent. So let's put -4 up there. And notice how my graph has now shifted to the right. And if I put +4 up in my exponent, notice how it has shifted to the left. So same idea as what we did with the quadratics. We have the horizontal translation in with the x. A plus takes it to the left, and a minus takes it to the right. Okay, so just to reiterate, when a number is added or subtracted in the exponent, that is a horizontal translation. And when we see an x minus that number, that equals a horizontal translation to the right. And if I have an x plus that number, that equals a horizontal translation to the left by that many numbers. Okay, a few more translations to look at. This time, let's look at the horizontal stretch or compression. So this time, we're going to multiply the x value by something. So if I make it 3x, it looks like that. And if I make it 1/3 x, it looks like that. So I can see that I have a horizontal stretch when I have a fraction in my exponent, and I have a horizontal compression if it's in my y-axis and I'm timesing it by a big number. So let's write that all down. Okay, so writing this all out, we have a horizontal compression when you have a number bigger than 1 times the x in the exponent. And we have a horizontal stretch when you have a number between 0 and 1 times the x in the exponent. Okay, good. Okay, I believe our last transformation to look at is reflection. So this is when we put negatives either in front of the exponent, in front of the function, or in front of the exponent. So let's see what happens there. If I put the negative in front of everything, so I have a reflection in the x-axis. And if I put my negative up top in the exponent, I have a reflection over the y-axis. Okay, so let's just make sure we jot all that down. So this red function here is just my usual 2 to the x. When I put the negative in front of my base, oops, that's an x, I had a reflection in the x-axis. And when I had my negative up top here, in with the x, then that made it a reflection over the y-axis. Okay, so let's just type that one out. Negative in front of the function equals reflection in x-axis. And if I have the negative in the exponent, that is a reflection in the y-axis. All right, let's put it all together and finish this off. let's summarize everything all up. So our general form of our function looks like this. So that a value is if we have a reflection, so a negative a value is a reflection in the x-axis, and it is a vertical stretch or compression. So that is our a value. Our k value here, well, that's going to be our, if it's a negative, that is a reflection in the y-axis. And k is equal to our horizontal stretch or compression. So that's our k value. We have our d value, which is right here. So that one is a horizontal translation. And to finish it all off, we have our c value here. And that one on the outside is our vertical translation. Okay? So let's do a little bit of practice with that. Where you go, try the homework, see what you can do. And yes, you can always graph things in decimals, just like I've been doing, in order to see how things look.